Okay, so picture the periodic table. Think of it like a big, organized city. You've got one neighborhood, the metals, that's all shiny skyscrapers, buzzing with energy, super conductive. And then on the other side, you've got the non-metals, kind of the quiet, insulating suburbs. Everything seems to have its place, right?
But what happens when you get to the border? The elements that have a house right on the dividing line? They're not quite downtown, not quite in the suburbs. That's the question, and that's exactly what we're going to unpack in this explainer. So here's the plan. We're going to meet these borderline elements, figure out their dual identity, and then look at some of their really wild and wonderful structures. After that, we'll zero in on two big ones, silicon and boron, to see how they totally changed our world. And we'll wrap it all up by talking about why being in between is actually their superpower.
All right, let's jump in. First up, let's meet the elements holding down the fort on that borderline. They're the official border patrol of the periodic table, the metalloids.
There are 6 of them, and they create this really cool diagonal staircase that slices right through the periodic table, separating the metals from the non-metals. We're talking about boron, silicon, germanium, arsenic, antimony, and tellurium. These guys are living life right in the middle, caught between two completely different worlds.
So what does it actually mean to be on that border? Well, chemically speaking, it means you've got a bit of a split personality.
And here's the perfect example of that identity crisis. I mean, look at them. They look like metals, right? They're shiny, they're solid, but when it comes to their behavior, totally different story. They act like nonmetals. They build these strong crystals by sharing electrons, and they're not really into forming the kind of ions that metals love to make. It's like they cherry-pick their favorite traits from both sides of the family.
This whole split personality thing gives them their most famous superpower. They're semiconductors. Now, in a metal, electrons just flow like water in a river. Easy peasy. But in a metalloid, the electrons are held on a slightly tighter leash, so they can conduct electricity, but just not that well. And that's the magic trick. It gives us this incredible dial of control, which, as you probably know, is the absolute bedrock of all modern electronics.
So where does this weird behavior come from? The secret is all in the architecture, how their atoms decide to link up and build things. These unique crystal structures are everything.
Take boron, for example. It's not interested in simple little cubes. No way. Boron goes all out and builds these ridiculously complex, beautiful shapes called icosahedra. Seriously, just imagine a 20-sided die and stick a boron atom on every single corner. That's what we're talking about. Now, silicon and its buddy germanium, they do something different. They form what's called a diamond lattice. Each and every atom is locked into place, covalently bonded to 4 of its neighbors. This creates this super strong, super stable 3D grid. And that rock-solid, predictable structure? That's exactly why we trust silicon to be the foundation for our computer chips. Then you've got arsenic and antimony. Their thing is layers. They build these puckered sheets, kind of like graphite, where each atom is connected to 3 others within its own sheet. Think of it like a stack of papers, but the papers themselves are wrinkly.
And to round things out, we have tellurium. It forms these amazing infinite spiral chains. Just picture a long chain of atoms twisting around and around forever. So you see, it's the sheer variety of complex, strong, and honestly just weird structures that really makes the metalloids so special.
Okay. These structures are definitely cool to look at, but what's the point? What do they actually do? Well, let's pivot to the undisputed rock star of the metalloids and see how its unique structure literally built the world we live in today.
Yeah, it's pretty much impossible to overstate how important silicon is. I mean, it is everywhere. It makes up nearly 1/4 of the mass of the Earth's crust. The only thing more abundant is oxygen. It's in basically every rock, all the soil, all the sand on the beach. It's the stuff of our planet. And this gets at why silicon is so different from its upstairs neighbor on the periodic table, carbon. Think about it. Carbon dioxide is a gas, little individual molecules floating around. But silicon dioxide, that's sand. It's quartz. It's a rock-solid solid. And that's because silicon loves to form these huge, sprawling networks with strong single bonds. It's a builder. It would rather create a giant, stable skyscraper than a bunch of tiny, flighty molecules.
But to tap into its amazing semiconductor powers, we need silicon that is ridiculously pure. And the way we do that is with this ingenious process called zone refining. It works like this. You take a silicon rod and you heat up just one tiny end of it until it melts. Then you slowly drag that melted zone down the entire length of the rod. As that little pocket of molten silicon moves, it acts like a magnet for all the impurities. They just dissolve right into it and get pulled along for the ride. And when you get to the end, you just lop off the dirty part. It is such a clever, elegant way to literally sweep the impurities out.
And what you're left with is this ultra-pure silicon, which is, without a doubt, the single most important element in the entire computer industry. This is the stuff that transistors, solar panels, and every single computer chip that powers our modern lives are made from.
But hey, silicon doesn't get to have all the fun. It's not the only metalloid hero out there. Let's shift gears and talk about boron, and an application you've probably used without even thinking about it, maybe even in your own kitchen.
Now, unlike silicon, which is just lying around everywhere, boron's a little more elusive. You have to go looking for it. You'll typically find its compounds near volcanoes or in the dried-up lake beds of deserts. Think places like California.
So what's so great about boron? Well, we use it to make borosilicate glass, which you probably know by its famous brand name Pyrex. See, when you add boric oxide into the glass mixture, something amazing happens. It drastically lowers how much the glass expands and contracts with temperature changes. What does that mean for you? It means it resists thermal shock. You can pull a baking dish straight out of a hot oven and put it on a cool countertop and it won't shatter into a million pieces. That's boron, doing its thing.
All right, so we've seen who these elements are and we've seen some of the cool stuff they can do. So let's zoom out and pull it all together. Let's talk about why being stuck in the middle is actually their greatest strength.
This really breaks it down perfectly. It all starts with their electronegativity. That's just a fancy term for how much they like to hog electrons in a chemical bond. Their value is right in the middle, which is why they act like both metals and nonmetals. Then there's how tightly they hold their electrons. Not as loose as a metal, but not as tight as a nonmetal. That's the sweet spot that makes them such perfect semiconductors. And finally, their love for building strong shared covalent bonds. That's what gives us those unique, super stable structures we can use to build our world.
So in the end, the real power of the metalloids is that they're ambiguous. They just refuse to be put in a box. And that refusal to be just one thing or the other isn't some kind of flaw. It's their defining feature. It's exactly what makes them so unbelievably essential.
And that leaves us with one last question to chew on. The metalloids prove that some of the most amazing, world-changing properties can be found right on the border, in that gray area between neat categories. So you have to wonder, what other in-between materials are out there right now, just on the edge of what we understand, waiting for us to find them and change the future all over again?